Let's start with the second half of today's lecture. What I wanted to do is I wanted to show that SLNR is a Lie group. And clearly it is a subgroup of GLNR. And if I can show that it is a submanifold as well, then it is a Lie group, as we have seen. So this is what I will try to do. First of all, I have recalled what the definition of a submanifold is. And I'm going to combine this definition with two principles. The first is to show that this map is projective. The tangent map of the determinant is a projective map from the tangent space of GLNR to the tangent space at 1 of R star. Which is really, can be identified, this is an open subset of R, and so the tangent space at every point can be identified with the ambient linear space. Then this will imply, by the submersion principle, this is the strategy of the proof, this will imply by the submersion principle that the fiber determinant inverse of 1, which is SLNR, is a submanifold at the identity element. I will postpone the proof of this and first use homogeneity to show that once you know that a subgroup is a submanifold at the identity element, then actually it's a submanifold everywhere. So let's first turn, let's call this A and B, and let's first use this principle of homogeneity. So first B. So A will give us that SLNR is a submanifold of dimension 1 less n squared minus 1 of GLNR at the identity element. And what I'm now going to do is I'm going to invoke homogeneity to show that it is actually a submanifold everywhere. So we postpone this. First, we are going to formulate a principle of homogeneity. And that principle says the following. Suppose that we are in the following situation, which has been sketched over there. G is a Lie group. And suppose that H is a subgroup. Then the following statements are equivalent. First, H is a submanifold at the identity element. And secondly, H is a submanifold at any element H of H. This is really a theorem, or maybe I should call it a lemma. And the idea is that if I have proved the surjectivity of that map, and I have proved this lemma of homogeneity, then I'm really done. Because then I will have shown that as a lemma R, it is a subgroup, it is a submanifold at the identity element, therefore by homogeneity it will be a submanifold everywhere. And then we have a subgroup which at the same time is a submanifold of a Lie group, and therefore it's a Lie group of its own branch. That's the idea. Is this clear? So let's give a proof of the lemma. But before proving the lemma, I want to do a bit of preparation, introduce some notation, for instance. And the preparation is about homogeneity. Suppose that G is a Lie group. This is preparation for B. Suppose that G is a Lie group, and suppose that A is an element of G, then we have an obvious map to pass from one point of the Lie group to another point, and this map is left translation by, which I'll call left translation by A. So define LA to be mapped from G to G, which maps X to A times X. So we may visualize the Lie group as a manifold like this, and then given a point X, then the multiplication map will map X to AX. And this is what's called left multiplication. Of course, there is a similar map for right multiplication, and we have to distinguish between the two because the group need not be commutative. So we also have an RA of X, right multiplication by A of X, which is X times A. And in general, that's a different map, but it may be used for the same purpose as I'm going to show you right now. Now this left multiplication, what can we say about it? First of all, LA is really X maps to mu of A comma X, where mu is the multiplication map. So we have a smooth map here, and we fix one entry, so this map is smooth in the remaining entry. So this is a smooth map from G to G. Smooth. Now clearly, it's also bijective. And its inverse is just multiplication by the inverse of A. If we first multiply by A, and then we multiply by A inverse again, then obviously nothing happens, because we are using the associativity of the group here. So this map is a bijection with this as its inverse, but for the same reason that LA is a smooth map, this is a smooth map as well. And that means that we have a bijective map, which is smooth, and whose inverse is also smooth, and therefore we have a diffeomorphism. So LA is a diffeomorphism. So we may use the multiplication, and the idea now is that we may use the left multiplication by the Lie group to compare the manifold structures at different points. And this is what I would like to call the principle of homogeneity. And we're going to apply this to in order to prove the result that a subgroup is a submanifold as soon as it is a submanifold at the identity element. So, what was the situation? So now we come to the proof of that lemma over there, what was the situation? G is a Lie group. H is a subgroup. Now clearly if H is a submanifold, then it will be a submanifold at each of its points. So one of the implications is trivial. So the only thing that I need to do is to show that if H is a submanifold at the identity element, then it is a submanifold everywhere. Assume H is a submanifold at the identity element. And what I want to do is to prove, so fix an arbitrary element. And what I want is now to prove that H is a submanifold at H. And if I can do that, I'm really done. Right? So now the idea is that we have our Lie group G, we have our subgroup H, and we know that H is a subgroup of the identity element. That means that there is a charge around the identity element, say chi, or an open neighborhood U. Chi should really be a charge to some Rn. So I could refine this a little bit. Submanifold at E of dimension, say, n. Then the claim is that this is a submanifold at H of the same dimension. N. So look at Rm as embedded in Rm in this way, n being the dimension of G. This is the image of the chart, and then what I want is that this intersection is mapped onto the intersection of Rm with chi of U. So this is what I know. I know that there is such a chart. So this chart satisfies, let me remind you that this chart satisfies the chi of U intersected H is the same as chi of U intersected with Rm. This is the meaning of H being a submanifold at the identity point. Now let's take an arbitrary point H. Then the idea is to use left multiplication by H to compare the neighborhood here to the neighborhood over there. So let's left multiply by H, and then we get a neighborhood over here. What is this neighborhood? LH of U. Well, clearly, because this is a diffeomorphism, so it's topological isomorphism, so open sets are mapped to open sets. So this is an open neighborhood of H. And it's the open neighborhood that comes about by multiplying U, every point of U on the left by H. So this is really HU. And now the idea is to use the inverse of this, which is a diffeomorphism, and compose it with this chart. And then we get a chart, a new chart, say chi prime, or chi at H, we could say, which is equal to the composition of chi with left multiplication by the inverse of H. So it's the inverse of this left multiplication. And this will produce a chart here. And this chart, of course, will have the property, or this is what we are going to show. We are going to show that this chart will have the property that it maps the intersection of H with HU onto the intersection of Rm with chi. So let's write it down. And this is really a consequence of the fact that H is a subgroup. quickly running out of chalk here. So I would like to ask, for instance, Uri, would you mind going downstairs to the reception and ask for some new chalk, because chalk is getting finished. Okay, great, thanks. Okay, so what do I want to show? I want to show that, so define this chart chi sub h as first applying left multiplication by h inverse, and then it's followed by the original chart, and then of course this maps hu to u, which is mapped to chi of u. So chi of h is really a diffeomorphism from here to here, being the composition of two diffeomorphisms. And now let's look at what happens to chi of h intersected with hu. Well, h is a subgroup, so h may be expressed as h times h. Left multiplication by h is a diffeomorphism, so in particular it's a bijection, and it preserves intersections. So this is the same as h of h intersected u. H times h intersected u. So now we have chi composed with left multiplication by h inverse applied to h times h intersected u. And then of course the h drops out. And then we have our original chi of h intersected u, of which we knew that this is chi of u intersected with Rn. But chi of u is the same as chi h of hu. So now we have produced a chart at h which straightens out h at the point h. And therefore, h is a capital H is a submanifold at the point h. Details of the proof can also be found in the lecture notes. But I hope that the idea of homogeneity is clear. Oh, that's great. Thank you. So may I introduce one of our assistants, Uri. You're being videoed. Okay. Is this idea of the proof is clear? I hope so. So now let's turn to the first part of the proof. We wanted to show that S and R is a submanifold at the identity element. And the first thing I'm going to show is lemma. I'm going to say something about the tangent map at the identity element of the determinant. And the claim is that this is going to be, so maybe I should introduce this. I'm viewing the determinant as a smooth map from GLNR to R star. And this is a smooth map. It maps the identity element to 1. And that means that there is a notion, a generalized notion of derivative, which is really, in this case, the same as the total derivative. Because we may, this is a map from the tangent space at the identity element of GLNR to the tangent space at 1 of R star. This is basic differential geometry. Now, GLNR is an open subset of the space of all square n by n matrices with real entries, an open subset, and therefore this tangent space may be identified in a canonical way with that ambient subspace. So, which is the linear space of all n by n matrices with real entries. And a similar observation here makes that we may identify this with R. And if we do these identifications, then the tangent map really becomes the total derivative of the determinant at the identity element. And now the lemma says that the total derivative of the determinant map at the identity element really is a linear map from here to here. And what is this linear map? This is the trace map, taking the trace of a matrix. So it is equal to the trace as a linear map from all matrices to R. Let me recall that the trace of a matrix is the sum of the diagonal elements. And actually I want to call this matrix H. So this is the definition of the trace, or in Dutch, spoor of a matrix. And I'm going to show that the determinant, which is a polynomial map and therefore differentiable, so it has a total derivative, and I'm going to show that the total derivative is the trace. Proof. Well, the total derivative, so let H be an n by n matrix. Then calculus in several variables gives us the result that we can determine the total derivative by taking a directional derivative. The total derivative applied to H can also be given as a directional derivative. Oops. So H is a general matrix, n by n, and then the total derivative of the determinant at the element I applied to H, how did I write it over there? Yeah. Is really the same as take the directional derivative of the determinant at the identity element in the direction H. Okay. Now, this is the ddt at t is 0 of the following expression. What I can do is I can write this as a polynomial and then organize on powers of t. And then what I will get is, first of all, 1, the constant term of the polynomial t. This is going to be a polynomial in t. The second term is t times the trace of h. And then we have higher order terms in t. Polynomial terms. So if we do the differentiation, then we will get 0 here. We will get trace h here. And we will get a polynomial without constant term here, because this is higher order terms than degree 1. So if we differentiate one time, then all terms will have at least degree 1. So if we evaluate at 0, at t is 0, we get 0. So we get 0 plus trace h plus 0. So this is the trace of h. And this proves the result. Now, so this is the end of the proof of the lemma. And the corollary of this, is that the tangent map of the determinant at the identity element, used as a map from here, or from the, well, let's say from the tangent space of G O N R to the tangent space of 1 of R star, that this is a surjective map, is a surjective linear map. Right? Because the trace, this is basically the trace. If I do the identifications over here, then the tangent map of the determinant became the total derivative. And this total derivative is the trace map. Now, if I prescribe any number, then of course I can find the matrix with that number as a trace. So that trace map is a surjective linear map. And that's the proof. But this means that the determinant map is what is called a submersion at the determinant map as a map. The determinant map as a map from GLNR to R star is a submersion at the identity element. And now it is a general principle that a submersion can locally be viewed as a projection, a linear projection. In other words, around the element I, this is the submersion principle. Around the element I, there is a coordinate patch such that this determinant map just becomes the projection map. But that means, in particular, that the fibers, so the pre-image of a particular element here, so I should draw a picture. Because this is knowledge from differential geometry that you should familiarize yourself with. And if you haven't already done so, you should do that. So the general result is as follows. Suppose that we have a manifold M, and we have a manifold N, and we have a smooth map F between those manifolds. And suppose that we have a particular point A here, and assume that the tangent map of F at A, which is a linear map from the tangent space to the tangent space at the image point, assume that this is surjective, then the statement is something like, so here we have F of A. The statement is something like, there exist charts with certain properties. The properties are as follows. There is a chart here, and there is a chart there. And so, and this chart should map to, say, subset of this form. And here, the chart over there, here, should map that subset to a subset of some are M here, some are N here. And of course we know, because this is a surjective linear map, that the dimension of this space is at most the dimension of that space, so we know that N is at most M. The chart, so the condition is that F should map this patch into here, which can always be arranged by first having a patch here and then making this patch small enough. And then if we do the translation by means of these diffeomorphisms, then F can be described as a map here. Let's say F tilde. And what should F tilde be? Now I've made a miserable picture. I'm sorry about that. I think it is better to do it like this. So to visualize this as one-dimensional manifold. And then the idea is that this F tilde should precisely be the projection onto a subspace along the remaining coordinates. So once you know that the tangent map of a map has this property of surjectivity, then you know that in local coordinate patches, this map may be represented by a linear projection. Now, of course, by the definition of a submanifold, this means that the fibers of the map are really locally at a submanifold. So that's the idea of the proof. And that's the idea of the submersion principle. Is this more or less clear? So that means that we're done. We have shown that, so I should say what the fibers of a map are. The fibers of a map are the pre-images of points. Right? So, okay, so we know that the determinant map from GLNR to R star is submersive at the identity element. And then the conclusion is that the fiber of the identity element, so by the submersion principle, this implies that the fiber of the identity element in R star is a submanifold of GLNR at the identity element. But this was as an NR. So we are done. In the exercises, one of the homework exercises, you are asked to apply this submersion principle once more to show that the orthogonal group is a Lie group. It's really also a submanifold of the general linear group. Now that I have gone through some of the things that you would need from a naive point of view to show that a subgroup is a Lie group, I think you will appreciate the following theory. This is a theorem that we really cannot prove yet, but we are going to prove this in the lectures to come. The theorem is as follows. Suppose that G is a Lie group and that H is a subgroup. Then the equivalent are the following statements. H is closed. By closed, I mean closed in the sense of topology. So G is a manifold, so it has a topology, and H should be a closed subset. And B, H is a submanifold. Hence, a Lie group. So this is really a very strong result, because in general it is quite easy to check whether something is a closed subset. For instance, let's do that. Let's apply this general result to SLNR, and then we will see once more that SLNR is a submanifold, but in an almost trivial way. So this is really a very strong result. So a review of SLNR. Well, the determinant is that from GLNR to R star, and it's continuous because of, well, it's basically polynomial in the matrix entries. So it's obviously a continuous map. And so that means that the pre-image of a closed set will be closed again. Well, the set consisting of the single element 1 is a closed subset of R star. And so we find that the pre-image of this subset is closed in GLNR. Now this is SLNR, which was a subgroup. So by the theorem over there, we conclude immediately that SLNR is a Lie group. Okay, and we can apply this same principle, and I'm going to finish up my lecture. We can apply the same principle to show that basically all of the classical groups that I wrote down are Lie groups. Let's do that. And for this, I need the following idea. That all of these classical groups are basically groups that preserve a bilinear form. It could be an inner product, definite or indefinite, Hermitian, or it could be symplectic forms, or, anything of that type. So, by way of it, let's first state a general principle. So suppose that we have a finite dimensional linear space let's take a finite dimensional linear space V. And let W also be a finite dimensional linear space. And suppose that we have a bilinear form from V times V to W. Bilinear form, so it is a map which is linear in each of its slots. Then there is a natural action of the general linear group of V on the space of such bilinear forms. If G is an element of GLNR, then I can define a new form, G dot beta, as follows. It is the form which, on two vectors x and y, we first apply the inverse of G. Well, for the purposes of this talk, we do not really need this, but I want to have a left action on the space of bilinear forms. Therefore, I've used this notation in the lecture notes. So we apply the inverse of G to x and y, and then we take the original bilinear form. So you could also say this is the pullback of, this is the composition of this map, which is really the pullback. Take this map and take then the inverse pullback and apply it to the bilinear form. That's really what it is. And now, what we can do is we can look at the stabilizer. So this is really an action, and from the theory of groups and their actions, we know that if we have an action on a space, and we take the stabilizer of a point in that space, we will get a subgroup. So the stabilizer in, and then we take, I'm saying GLNR, but I mean GLV, the general linear group of V, the group of all invertible linear transformations from V to itself. Then the stabilizer of beta in this group is the set of elements in GLV with the property that G dot beta is the same as beta. Now it's easy to check by hand that this is a subgroup. It is also easy to check by the same kind of methods that I used before, that this is closed in the sense of topology. And the reason is that this is really a continuous condition. So it's also closed. Details can be found in the lecture notes. But as a consequence, the stabilizer is a subgroup. Now let us give two examples of such a stabilizer. Is a Lie group. Sorry, it's a submanifold and therefore it's a Lie group. Now let us give two examples to show that this is really not just an abstract exercise, but gives you lots of examples of Lie groups. And we'll first start with the orthogonal group. So let's start with the orthogonal group. The orthogonal group is the stabilizer of GLNR, in GLNR, of the standard inner product on Rn. So here, let's take the standard inner product on Rn. So what is this? So this is our beta. Now, the standard inner product, of course, is given by inner product of x and y is x1, y1, up to xn, yn. And so it is the group of matrices that preserves the inner product between two elements. These are precisely the orthogonal transformations. Another way to characterize the orthogonal transformations. So G is an element of the orthogonal group, if only if the transpose of G is equal to the inverse of G. It's another way of saying it. But one way to characterize the orthogonal group is as the stabilizer of the standard inner product. Now, from the general principle, we know that this is a Lie group. End of story. So, we can do a similar thing, likewise, for instance, for the Lorentzian inner product on R4. So the inner product of signature 1, 3, which maps a pair x, y to x1, y1. This is all. I'll ignore any physical convention here. I always forget where to put the pluses and the minus, but there should, of course, be, well, let's do it. X4, Y3. So it is a standard inner product of signature 1, 3. So what is the stabilizer? Will also be defined as the orthogonal group of signature 1, 3. So this is just the stabilizer of this particular inner product in GL4. And by the general principle which we outlined about bilinear forms, which we outlined here, this is a Lie group. Let's take one step more. If we restrict to elements of determinant 1, then we usually put an S in front of everything. So SO1, 3 is the intersection of SL4 with O13. These are both subgroups, so the intersection is a subgroup. these are both closed. So the intersection is the intersection of two closed sets, and is therefore a closed set. So this is a closed subgroup, therefore a Lie group. And if you want to know about the other classical examples of Lie groups, please read the lecture notes carefully. So this is the theory for today.